to the picture language seminar. We're very pleased today to have Weinan. Until recently, he was professor at Princeton University in the Department of Mathematics and Applied Mathematics, but he went to Beijing and now is the inaugural director of the Beijing Institute for Big Data, and at the moment in a conference, so in a hotel, and we're very glad that he could join us and give a seminar online and tell us about a mathematical approach to machine learning. So Weinan, the stage is yours, and we look forward very much to your talk.
Thanks very much. Yeah, thank you. Well, let me start sharing. Well, thanks very much for the invitation. Well, I'm going to give a, shall we say, very brief mathematical, I would say mathematical introduction, but the mathematical theory is not complete. So I try to explain things from a mathematical viewpoint, but certainly there are lots of gaps in the formulation and theory, stuff like that. But I think it's important area, and it's a very promising area. So let me start with what machine learning can do. So machine learning can really do wonders. My first example is image classification. So what you're seeing is what is called CIFAR-10 data set. So these images contain some information. Actually, all the information belongs to one of the 10 categories: airplanes, automobiles, and stuff like that. And the task is to classify the images, meaning that for each image, we're supposed to tell automatically what the content is out of the 10 categories. So this is a very classical example. The second example, you are seeing pictures of human face, very high quality pictures of human face. But all these pictures of human face are fake, and they're generated by some machine learning algorithm. But what's amazing is that they're really very realistic looking. The third example is AlphaGo. So AlphaGo is, very well-known example, and it's built upon the principles of deep reinforcement learning. So reinforcement learning plus deep learning. I'll explain what deep learning is about later. But that's another very successful example. It can build right now, it beats all humans. Now, what's important is that all these three examples are really solving some mathematical problems. We go back to image classification. It's really so the function we approximate. The function is the function. Each image, finite piece of data of this function, we're supposed to, approximate this function. And the second example is approximating a probability distribution. We can think of the pictures of human faces as being a random variable in the space of images. And we don't know the probability distribution of that random variable, but we have a finite sample of that probability distribution, namely pictures of real human faces. So from that finite sample, we can actually approximate the underlying probability distribution sufficiently accurately and generate new samples. And these new samples are pictures of fake human faces, and that's what we are seeing. In the third example, we can formulate the Go game as some sort of a Markov decision process, and the optimal strategy of that Markov decision process satisfies some Bellman equation. So what's really done here is to try to solve that Bellman equation. Now we can solve that Bellman equation sufficiently accurately so that the strategy beats all humans. So the first example is about approximating functions. Second example is about approximating probability distributions. The third example is about approximating the solutions of Bellman equations. Now, approximating functions, probability distribution, and solving equations are really very standard problems in mathematics, particularly in computational mathematics. This is sort of my major. So this is what we've been doing all the time for a long time. But what is different here from what was done before in computational mathematics is that the examples we just are all very high dimensional examples. If we take the CFAR 10 problem, if you go back to the CFAR 10 problem, this thing here, now we're looking for a function in the space of images, and each image can be viewed as a point in a 32 by 32 by 3-dimensional space. 32 by 32, that's a number of pixels. Each pixel is a degree of freedom. And then 3 comes from the dimensionality of the color space of color. So each picture has a point in 3072 dimensional space. So we're really approximating a function in a very high dimensional space. And that's what's new in these examples. Now, if you go back to classical approximation theory, approximating functions, we have, this would be a typical theorem. In order to explain this theorem, let's first define some numbers. D is the dimensionality of the function we're interested in. And M is the number of degrees of freedom, number of free parameters. And H is the size of a mesh, because we're talking about, here we're considering piecewise linear approximations. So piecewise linear approximation over some mesh. And the typical size of the mesh is called H. And H is related to M by this relation. Just think about, say, a unit cube and putting points uniformly on the unit cube. Then the mesh size is related to the total number of free parameters by this relationship. And then this would be a typical theorem in approximation theory, namely the error in the best approximation measured in an L2 norm is bounded by H times the H2 norm of the target function. So if you look at this, if we want to reduce the error by a factor of 10, we need to reduce the size of H by a factor of 10. That means we need to increase M by a factor of 10 to the D. Now, if D is equal to 3000, this is a really huge number. So this is the classical difficulty called curse of dimensionality. Now, this problem is common to all grid-based or fixed basis-based algorithms. Essentially, all the algorithms we had before suffers from the curse of dimensionality, whether it's piecewise linear approximation, polynomial approximation, wavelets, trigonometric approximation, all that kind of algorithms suffer from curse of dimensionality. Now, curse of dimensionality is not just for algorithms, it's a common difficulty for lots of problems. It's a problem in statistical and machine learning. In statistics, we talk a lot about linear regression, but beyond linear regression, when we talk about nonlinear regression, then we very quickly we face the COD problem. Quantum many-body problem, solving Schrödinger equations, that certainly has a curse of dimensionality problem. Classical many-body problem, if you want to solve the protein folding problem, for example, also has a COD problem. And then control theory, dynamic programming, well, that's where curse of dimensionality, the terminology was proposed by Richard Bellman in 1958. And then, combinatoric optimization, there's an issue of combinatoric explosion, and that's very similar to the COD problem. Now, before
just a question. Just a question about the COD.
Yeah.
is it because like that's the best inequality we can prove? Or is it because that inequality is actually quite tight and we have counterexamples that sort of show, this is really the best you can do?
This is really the best we can do. This is actually, we can actually show, that this is almost equivalent.
I see. Thank you.
There's actually, this is the, I'm going to talk about this in a minute. This is called the direct approximation theorem. Says that the best error is bounded by something. There's also a inverse approximation theorem, which says that if a function satisfies this function must be H2. This quantity must be finite. So it's almost if and only if. Now, before deep learning, what do people do in order to deal with the cursive dimensionality problem? Well, let's give, here is a typical example. We have a function of many variables. Think about this as a wave function in quantum mechanics. Well, there is a well-known approximation called Hartree approximation. It simply does this. It replaces this function of many variables by products of functions of one variable. Well, this is the most commonly used version is the Hartree-Fock. That's the sort of asymmetrized, anti-symmetrized version of this, because when we talk about fermions, it needs to be anti-symmetric. But anyway, this is the basic idea. And in dynamic programming, this has got another name called approximate dynamic programming, but it's basically the same idea. In statistics, people talk about generalized linear models. So approximate these functions by, well, I should have got the coefficient here, alpha k. So alpha k, fk, and these fk's are some pre-chosen functions. Well, naturally, these fk's, these basis, some sort of basis functions should be chosen very, very carefully. In AI, these functions are called features. So choosing these features becomes very much an art. So the construction of these features, intuitions and experience, and etc. For example, in computer vision, there's a very well-known set of features called SIFT, scaling invariant invariant features. Okay, so anyway, this is very much of an engineering engineering problem. So this is what people do. This is kind of a typical thing people do before deep learning. Okay, now apparently it seems from the examples that's just illustrated, there are many more examples. It seems that deep learning can be a very powerful tool for attacking a COD problem. So naturally, we have two questions. First, can we use deep learning to solve other problems, not just problems in AI, but other problems, say the kind of problems that I just discussed? And that's the first question. The second question would be, why is deep learning so powerful in high dimension? So let me, before I discuss these two questions, let me first give you an overview how the procedure people do when in deep learning. So here we're trying to we're given some data. No, we're given some data. This is the problem here. Sorry. Some data. We try to use this data to approximate the underlying function, the underlying target function. So we're giving the values of a target function at finite set of points, and we try to use that information to approximate or the underlying function f star. So that's what I want to do. So there are three components. The first component is to choose a hypothesis space. Now, hypothesis space is just a set of functions, set of trial functions. We're going to use that function to approximate the target function f star. For example, we're going to choose these guys. So linear combinations of sigma W transpose X, where sigma is some nonlinear activation function. For example, this nonlinear activation function. And this is called a two-layer neural network. because we've got two sets of coefficients, AJs and WJs. And these are the free parameters we're going to use to approximate our target function. And usually we use theta to denote the parameters. So this is the first step, choosing a hypothesis space. The second step is to formulate an optimization problem that we're going to solve in order to find the best approximation. For example, since we're given a finite set of data, this will be a very natural objective function to minimize so that we can. Third example is to choose an algorithm to solve optimization problem. For example, the simplest is gradient. That's just this. You each step the gradient and you move in the direction of the. I should have a theta. Sorry. Notice that if you do, then step each you need to compute this and this n terms. N, I didn't say n is the data set. N is the set. If you got a huge, this is the huge sum, so that's going to be expensive. Instead, what do we do is to just pick a typical term, randomly sample a term from this sum, from this average, and use that to represent this average. And this is called stochastic gradient descent. That's this. It turns out this SGD, stochastic gradient descent, is not just a much more efficient algorithm, and it actually performs better in practice. So that's one of the mysteries why this performs better. Better meaning that it performs better on the new data set on new data, the data that you didn't use to train the test data. Okay,
sorry, your connection broke up a little bit. It performs better than what? I didn't quite hear you.
Perform better than the gradient descent. Than this.
Okay, I see.
It's cheaper and it's better. So it's cheaper. That's easier to understand, and we actually can put that in very precise terms. But the reason why this is actually better, that's a bit of a mystery.
Well, do I understand that you don't really want to get the exact answer anyway, given a certain data set, right? That would be a problem.
Meaning, what do you mean exact?
You wouldn't be able to generalize it. It wouldn't generalize well.
When you say exact,
descent somehow enables you to generalize.
Yeah,
you get a new data set. Otherwise, you might get a polynomial fit, which is too good, and then that's not going to be good for the next sample.
Okay, that's a very good point, and I'll explain that later. But what often happens right now is that we actually fit this perfectly, and then what happens in practice is that the free parameters m is much bigger than n. M is much bigger than n, so there are lots of set of parameters for which this fits exactly, and then but out of these huge number of parameters, actually, huge manifold of parameters, we want to choose those that generalize well.
Yeah, I thought the gradient descent was better for, you're never going to get the gradient descent is not going to converge to your actual minimum, right? In general, because you got a highly non-convex function.
It does.
It does. Okay.
It does. Yeah.
Okay.
It's just that may converge to a bad global minimum.
Okay, meaning
that it's okay. This is zero. It fits all the data, but it doesn't generalize well.
Yeah, that's what I'm saying. Yeah.
So that's sort of the key here. So why it seems that doesn't seem to happen so often. We can always, by tuning the parameters, tuning the algorithm, tuning the hyperparameters in the algorithm, we can actually avoid that situation. That's one of the mysteries. The so-called implicit regularization. That's one of the mysteries. Okay, but I'll explain that a little bit later. So let me first give you some examples that that we can use deep learning based algorithms to solve some of the other COD problems that we face. And the first example is stochastic control. This is actually the very first example when the people use deep learning to solve problems in scientific computing or computational science. Anyway, so we're given this stochastic control problem. This is the dynamical system. This is the Xi. I hope you see my mouse. Xi is the noise, and A is the control. Z is the states. V denotes the states, and it wants to choose the control to minimize this expected cost, running cost, terminal cost. So what's important is that this is a stochastic optimization problem. The objective function is some sort of expectation. So that's important because we can readily use SGD. So we look for feedback control, meaning that control is a function of the state. And let's just abstractly think about approximating this function by some neural network. Never mind what the details of that neural network. And just plug in, then our problem becomes this. We look for optimal parameters that minimizes this expectation subject to this dynamical system. The dynamical system, we view this dynamical system as sort of a constraint. So if you look at this, we've got an optimization problem, which is the stochastic optimization. I just said that, but I'm just repeating that the objective function is an expectation. And then this dynamical system here, if you're familiar with ResNet, residual neural network, very much like the residual neural network. So this is not very far from the standard supervised learning problem. So that's why we thought about this. We sort of choose this as the starting point, the very first example to develop deep learning based algorithms. But anyway, it works like a charm. This is a made-up example. This is some sort of energy storage, high dimension. The dimensionality is like 3 times the number of devices. And then you can see as iteration goes on, it converges nicely, and this is very, about the size of the error. Okay, that's the second example. I'll go through this quickly. I mean, if you don't get the details, that's fine. I mean, I just want to give you an impression that we can develop deep learning based algorithms to solve these problems that we couldn't do before. We really couldn't do before. So here we're solving some nonlinear PDEs. And let's just reverse time. This was the initial value problem. After reversing time, it becomes a terminal value problem. And we prefer terminal value formulation because it's much easier. It is easier to write down some sort of stochastic reformulation of this. So I claim, and this is actually proved by Padu and Peng, that this PDE problem is equivalent to this very much like stochastic control problem. So we're minimizing this, the mismatch between the terminal value and the value of the Y process. And Y process satisfies this so-called backward stochastic differential equation. This is a very interesting stochastic differential equation because it's got one equation, but 2 unknowns. Y is an unknown and Z is an unknown. What Padu and Peng proved is that this SGD has a unique adapted solution as long as F is Lipschitz. So I think that's a remarkable theorem, but it's a theorem. So roughly speaking, that Z is almost like a Lagrange multiplier for the constraint that the process needs to be adapted. And the connection is as follows. Given the solution of this PDE, Y, the process Y, is given by U, evaluated at the process X. And the process X is the usual standard diffusion process. And the process Z is given by this. This guy is very much like the control. So, as I said, the PDE problem is turning into very much a stochastic control problem, minimizing some expectation subject to dynamical constraints. So we can apply the ideas in the previous slide and develop an algorithm for solving these kind of PDEs. So we call this we call this deep BSD method. Anyway, it's not. And this is an example. So consider this simple linear quadratic Gaussian control problem. The control is the M here. This is the Wiener process, and lambda is the parameter. But now we're going to solve this problem in 100 dimension, high dimension. Now the objective function, the cost function, is the standard cost function. Now for this control problem, one can write down the Hamilton-Jacobi-Bellman equation, and it's just this. For this Hamilton-Jacobi-Bellman equation, there is a Hopf-Koh transformation that turns this into a linear PDE. If you don't know about Hopf-Koh, that's fine. But from Hopf-Koh transformation, you can write down the exact solution, and that's just this. And we can use this exact solution to calibrate the deep BSD method, and that's shown here. The horizontal axis is the parameter lambda, and the vertical axis is the value of u at some random point. You can see it agrees pretty well. And we developed my student actually, former student Ji Chun-Han, he developed an open source platform that people can use these tools to play with high dimensional PDEs. So now solving high dimensional PDEs is becoming a fashion in applied mathematics. My third example is molecular dynamics. Now, molecular dynamics is a very common tool in computational material science, physics, and particularly chemistry, and material science, and even biology. It's just solving. Well, what's done is to track the trajectories of each atom in a material or in a molecule by solving Newton's equation. The difficult part here is the potential energy function that describes the interaction between all the atoms. And because the interaction of the atoms is sort of through, mediated by electrons, and the electrons really obey quantum mechanics. So this is really a very complicated problem, and V is a complicated function. So classically, there have been two ways to get V, or get the force. One is to calculate the force on the fly by coupling to some quantum mechanics model, density functional theory. So this is called Copernicus, was created in 1985, I think a very fundamental piece of work. So this is very good, but it's limited to like 1,000 atoms. That's really the limit. To put all the computational resources in high-performing computers. High-performance computing, you can handle like 1,000 atoms. The other approach, much more popular approach, is to just guess this function. A classical example is Leonard Jones. But guessing such a function is certainly very complicated. So this is efficient, but not reliable at all. The new idea is that we're going to use quantum mechanics models to supply the data, and then use machine learning to learn to approximate this function V, and then do molecular dynamics. Well, there's lots of technicalities that's involved to implement this program, but that's been solved really pretty well. For example, how do we generate the data? That's one big issue. How do you generate the data in order to get a model that we can trust as much as we trust Schrödinger equations? So that's very much an issue. But we've developed algorithms to solve these problems, and then you can see that the machine learning model, the so-called deep potential, we gave this name, not very creative name, but deep potential molecular dynamics. The accuracy over a very wide variety of systems, from small molecules, this is aspirin, this is ethanol, to big molecules, this is pyridine, pyridine 1, pyridine 2, to simple metals, simple alloys, to very high entropy alloy, alloy with 5 components. can see that the accuracy is pretty much comparable to the accuracy of the underlying density functional theory model. And by combining with high performance computing, perform molecular dynamics with ab initio accuracy, with quantum mechanics accuracy for systems up to like 100 million atoms. So this is last year's ACM Golden Bell Prize. Well, it's prize for high performance computing. But what's really, what this really demonstrates is that now we can do molecular dynamics, reliable accuracy with reliable molecular dynamics for very large systems. That doesn't mean we have already solved all the problems. We've solved the problem with the spatial scale. We can solve very large systems, but we still have a problem with the temporal scale, because in reality, in many of the applications, such as chemistry, the kind of processes we're interested in, for example, chemical reactions, are rare events. So they don't happen very often. They happen very rarely. You have to, try many steps in order for one event to happen. And that's still an issue. We're still working on that. Again, we've developed open source platforms for people to play with. And actually there's lots of people who are doing this. Okay, now, I give you an example of classical molecular dynamics, but actually over the hierarchy of fundamental physical models, from basic Schrödinger equation to density functional theory, to classical molecular dynamics, to coarse-grained molecular dynamics, to Boltzmann equations used in aerospace engineering, to continuum mechanics such as Navier-Stokes turbulence and stuff like that. This is the whole hierarchy of fundamental physical principles. There's, one can imagine using machine learning, using deep learning to speed up, to speed up, to develop more efficient algorithms. And actually, we've done quite a number of those, for Patrick Falk, for density functional theory, for sampling high dimensional space, et cetera, et cetera. We've, also other people have done a lot of work along these lines. My former students and I, we wrote in a sort of a review article in Physics Today that discusses using machine learning to develop new physical models that's both reliable and also interpretable. People often get the idea that machine learning is black box, so therefore it's very difficult to develop interpretable models. That's not the case. That's not the case. One can develop a reliable and interpretable model. New physical models using machine learning. And this article given a summary of that. Anyway, so that's the first point I want to say.
I have a quick question.
Yes.
Have you tried it on metadynamics? Metadynamics is it's again a very specific case of molecular dynamics where you can have.
Yes. So this is the reinforced dynamics. The metadynamics is great, but it only works for like 3 or 4 degrees of freedom. If you want to have coarse graining a system with like 100 degrees of freedom, metadynamics doesn't work. And what's work is this called reinforced dynamics. That's the replacement of metadynamics in the case when you have many coarse grained variables.
Okay.
And
what does reinforced dynamics mean?
I mean, reinforced what?
Yeah, what does reinforced dynamics mean? What is that? Okay. I don't understand the meaning of that statement.
So the name is created because of some analogy with reinforcement learning. So there's some sort of reinforcement in the dynamics, in some dynamic. You sort of learn on the fly. As you improve your learning, you're performing better and better. Using what you've learned to guide your search. So metadynamics is about, search very high dimensional space and compute free energy at the same time. So this is in that spirit, but we're sort of learning learning free energy on the fly, and then we use that thing to use the approximate free energy to help guide our sampling, and then improve the free energy at the same time. And then there's neural network involved.
In other words, you're using reinforcement machine learning techniques for dynamics.
Yes, yes, certainly.
Okay.
They
But again,
kind of analogous with reinforcement learning, but not exact reinforcement learning at all. So this is published in 2018 Journal of Chemical Physics. We have another paper which has come about this, which is going to be published very soon in Nature Computational Science. You're interested in. So you can use this to fold small proteins and to refine protein folding, to study some chemical reactions, stuff like that. If you have a good, reasonable coarse-grained variable. Okay, so now I want to turn into some mathematics. Now, first is understanding the mystery. We have two questions. The first is to understand mysteries about machine learning. There are two major mysteries. One is why does it work at all in such a high dimension? Two, why is it so fragile? Because it really requires extensive parameter tuning. So why is that the case? The second question, can we find better formulations of machine learning? Something like performance equally well, but much more robust. Okay, so that's the two sort of issues that we have in mind. I'll start with the first. Why do things work in such a high dimension? We do have an example, very successful example in high dimension. That's computing integrals. So Monte Carlo sampling in statistical physics, we can calculate integrals of millions of variables quite routinely, and that's very remarkable, even though we sort of forgot about how remarkable it is. And that's because we have Monte Carlo sampling. If you do usual quadrature, it has cursive dimensionality. If you do Monte Carlo, then the error, the error goes like 1 over m. There's no 1 over d in the exponent. So it means the convergence rate is independent of dimensionality. Of course, this coefficient, the variance, could be very large. So that's why we have to do a lot of variance reduction. So what do we want to do? So this is about computer integrals. Of course, we're not computer integrals. We're approximating functions. So what do we like to do is to have something like this. Namely, the error is bounded about very much like this. I wrote it like to be a norm, but I wrote it like no. So that's what we want to. Question is, can this? What? This is. If I.
You're breaking up. Maybe you can go back for a little bit.
Here.
The bottom of the slide.
Here.
Yes.
See something? Is there a question here about this slide? Well, I think.
No, we just could not hear what you said at the end.
Oh, okay. So I wanted to say, so we want to have this, right? We want to have this kind of a error control. We want this to be true. The question is, can this be true? For what kind of hypothesis space that this holds? And if it is true, we like to calculate this quantity here. We like to have an expression for this quantity.
Before you had the Laplacian there.
There's no Laplacian here. Sorry. So are you referring to the classical?
Yes. What is the? I see. What is?
Okay. Before, let me go back. This is helpful. Before it was this. So it was Laplacian of m. You can think of this as Laplacian f star over m to the 1 over d. The problem is that there is a 1 over d. So now I don't want to have the 1 over d. I want to have this, sort of motivated by this. This is sort of analogous to this.
Good.
Looks like the internet right now is bad.
Go ahead. We'll see what happens.
Excuse me, Professor. Should
Yes.
this norm with respect to the F, not the F star?
No. Okay, there should be FM here.
Okay.
Target function. F star is the function we're interested in, so this should be F star.
Okay, I see.
Not-
Thank you.
Now, if you, okay. Okay. So let me try to give you an intuition. Let's see whether this is convincing. So let's take a function like this, a function expressed by its Fourier transform. So A will be its Fourier transform. Now, associated with this representation of F star is the usual FFT, right? We can approximate this by this expression, where omega j is on a uniform grid. That's sort of the fast Fourier transform. And this is no good because it suffers from cursive dimensionality. That's what I said before. Now, imagine that F star is not expressed in this way, but expressed in this way. The only difference is that we replace dw by pi of dw, where pi is a probability distribution. That's the only difference. But then this guy can be written as an expectation. And then we can do Monte Carlo, meaning that we can approximate this by Monte Carlo sampling like this. And the error obeys this. That's what I discussed before. There's no cursive dimensionality. Okay, what's important is that this expression here, this FM here, is nothing but a two-layer neural network with a special activation function, sigma, that's given by the exponential. So this is a two-layer neural network. Well, if I write it as this, if I write this as AJ and use the sigma here, then this is what I said before, the two-layer neural network. So what I'm saying here is that if a target function can be expressed like this, then it can be approximated by a two-layer neural network with an approximation rate that does not suffer from the cursive dimensionality. So the question becomes, what kind of function can be expressed like this? So there's a big difference between this expression and this expression. So that's what I'm saying. So let's now give an example. So consider two-layer neural networks. Now we're considering the usual kind of two-layer neural networks, meaning that the activation function is this. This is called a ReLU activation function. This is the most common activation function used in practice. Now, I want to ask, for this kind of a hypothesis space, what is the set of functions that can be efficiently approximated by this kind of a two-layer neural network function? In order to address that question, we're going to limit our attention to functions of this form, functions that can be represented as, a probability, so where rho is a probability distribution in the space of parameters A and W. So this is natural because this is like the continuous version of this. And this can be expressed in expectation. Okay, so we're gonna consider functions of this form only, and associated with functions of this kind of functions, we can define a norm, and this norm, not necessarily a norm, but let's call it a norm anyway, which is some sort of expectation. You need to take an infimum here because the rho is not unique. So we take the infimum over all such rho. And these kinds of functions, the functions for which this quantity is finite, we call that barren function. to sort of honor the work that's done by Baron. One of his theorems will be presented in the next slide. Okay, let me add a point here. So you're going to see that we prefer representing functions with some kind of a probability distribution. Okay, and there's an underlying practical philosophy, namely that in these machine learning or deep learning models, what's important are not the specific values of the parameters that we found, but rather the probability distribution of these parameters. Because each time when you train these neural networks, each time you reinitialize, right? And you're going to end up with a different set of parameters. You're not going to recover the same set of parameters. So specific values of these parameters don't matter so much. It's the probability distribution for these parameters that's important. So that's also one of the reasons why we prefer to think about probability distribution for the parameters. Anyway, so I hope I made the point clearly. So one natural question is, what kind of functions admit such a representation? And there's theorem proved by Baron and Kolosowski, which says that if this quantity is finite, so where f hat is the Fourier transform of f. So if the Fourier transform decays sufficiently fast such that this quantity is finite, then this f can be represented in the way that we had before, and the Baron norm is this quantity here. Okay, so this is a general theorem proved by Baron and Kolosowski. Now, this is not a very satisfactory theorem because the condition depends on dimensionality. So a very interesting question is, what is the gap between these two quantities? So what are the functions for which this quantity is finite? And what are the functions for which this quantity is finite? Certainly, this is a bigger class than this class. By the way, these are the classes of functions that considered by Baron. Baron didn't actually consider these classes of functions. We consider these functions, but we still name this class after Baron, and seem to have created some confusion. Now, let me give you a specific example. If you could, this function, the norm of x, this function is a Baron function. But this function, distance to the unit sphere, is not a Baron function. That's because we can characterize the singular set of all Baron functions. That's a paper, this paper. And we're going to show that this guy cannot be a Baron function. So this is actually a quite interesting question, but no. So why do we define this class of functions? Why do I claim, why are we interested in this class of functions with this funny norm? Well, that's because, that's the right class of functions for which two-layer neural networks can approximate efficiently. Namely, we have the direct and inverse approximation theorem. The direct approximation theorem says that if a function, then it can be approximated by two-layer neural networks with the expected convergence rate. And conversely, if a function can be approximated by two-layer neural networks with some uniform bounds, then this target function must be a Baron function, and the Baron norm is bounded by the uniform bound. So these are the kinds of approximation theorems we would like to have in order to identify the class of functions that can be approximated by a specific set of neural network architecture efficiently. So that's only an approximation theory. That's assuming we know all the information about F star. But in practice, we don't know all the information about F star. In practice, we only know a finite data set, training data set. So can it happen that our neural network model fits the data on the training set very, very well, but does the poor job outside the data set. So can that happen? Well, that was the question that Professor Jeffrey asked in the beginning. Well, that's a classical example. So here what's done is that we are trying to interpolate, perform polynomial interpolation over a uniform mesh. So this is a uniform mesh. We're just doing a polynomial interpolation, and that's the result. That's the red line. The blue line is this function, very nice, smooth C infinity function. But you can see that in polynomial interpolation fits the data perfectly on the training data set, but does a very poor job, particularly at the boundary outside the training data set. This is called a wrong phenomena. We certainly don't want that to happen. So to measure the difference between the training error and the testing error, so we want these to be close. At the first sight, you might think, wow, this is just the Monte Carlo approximation of this. So therefore, the difference of the two is like 1 over square root of n. That's not true, because the theta, the optimal parameter, theta we're interested in, comes out of the training. The training process involves the data. So this is certainly not, lots of correlation in here. So the argument we used before doesn't work. So therefore, we cannot do that. The only, well, almost like one of the most powerful strategy is to look at the supremum of this difference over the hypothesis space. And it turned out the supremum is very well controlled by a quantity which is called Radamel complexity. It's controlled above and below by Radamel complexity. And the Radamel complexity is defined as follows. Basically, it measures the ability, okay, first of all, it's defined for a set of functions for a hypothesis space with respect to a training data set. It measures the ability for that set of functions to fit random noise over the training data set. So if one can fit random noise over the training data set very, very well, that means the complexity of the hypothesis space, the set of functions is very big. Then this is big. Now, for example, if H is like a unit ball in the space of continuous functions, then this quantity would be order 1. Because we're going to fit every data point perfectly well. So this will be n. So 1 over n, and then times n, that'd be order 1. Remember, we want this to be order square root of n. We want this to be like 1 over square root of n, because this was the kind of quantities we're interested in. The difference of the two is the quantity we're interested in, and the best we can hope for is something like 1 over square root of n, almost best, something like 1 over square root of n. But for continuous functions, it's like 1 over n. But I gave you the argument. If we consider a unit ball in the space of Lipschitz functions, for continuous functions, it's order 1. If we consider unit ball in the space of Lipschitz functions, then one can show the Radamel complexity is 1 over n to the 1 over d. So it's not 1 over n, it's better than 1 over n, but there is a 1 over d. So this is another form of cursive dimensionality. This is a cursive dimensionality for the size of the training data we need to have. So we don't want that to happen either. Now, luckily, for the barren space we just defined, there's a theorem proved by Bach, which shows that really the Radamel complexity is 1 over square root of n, sort of the best we can hope for. Okay, combining these two results, then we can show that if we regularize the empirical error, the training error, by this regularization. And so here, there's a standard factor. If you're familiar with machine learning, you know that this is a standard scaling factor. Lambda is just some parameter here, positive parameter here. And this norm here is defined as follows. It's almost like it's the Barron norm for the neural network. And anyway, for this particular regularization, one can show that all global minimizers, the testing error for all global minimizers satisfies this error estimate. There is a standard term that comes out of concentration inequality. So for these kind of theorems, one always has to use concentration inequality, and then you have this. So the theorem always says something like this, that for any delta bigger than 0, if lambda is sufficiently big, bigger than some fixed constant like 4, with the probability of 1 minus delta over the choice of the training data, the following result holds. Yeah. The right-hand side, so the testing error is bounded by 2 terms. The first term is like 1 over m, second term is like 1 over square root of n, and the third term is a small term coming out of the concentration inequality. So you can see that this is sort of the best we can hope for. And then the coefficient is like the Barron norm. And this kind of theorems can be proved for other situations too. For example, the so-called, so this is like the 2-layer neural network model. The random feature model is like 2-layer neural network, except that this WJ is no longer a training parameter, but rather it's fixed at some random values. So that's called a random feature model. So for the random feature model, the Barron space is replaced by producing kernel here. Works. I didn't explain very popular model. The Barron is replaced by so-called fluid space. Multi-layer neural network, 3-layer, 4 networks. It's not complete on a pretty far. That's actually very. We tried something called, but I don't think that's the right answer. We had the paper for this. Now, what is something like this? Arithmetic terms, error is bounded by m plus n, so estimation error. Okay, so that's sort of not explain. This does not, it says solution hypothesis space. Does not tell us optimization we had before can actually find these nice solutions. As a matter of fact, sometimes it doesn't. So that's another question. So why, by tuning the parameters, we can actually find these nice solutions? So that's another question that's really not understood, not completely understood. So I want to show you this example that I think partly explains why one needs to tune the parameters so hard, namely why the result is so sensitive to the choice of the hyper parameters. And look, figure here. What's plotted here is the testing error in over m, log of m and log of n. So remember, m is the number. So this is for 2-layer neural networks. For 2-layer neural networks, so m is the number of neurons, and n is the size of the training data, the size of the training samples. So if you look at this thing, there is a phase transition between this phase and this phase, and this is the good phase. This is the phase, if you look at it, this is the phase where the error is small. This is the phase where error is big. If you are not so lucky and you have you choose a point, your architecture, neural network architecture falls in this part, then the error is going to be big. So you have to tune your architecture so that it falls into this region. Now this is only a 2-layer neural network. You can imagine for multi-layer neural networks, this phase diagram is going to be much more complicated, and your tuning task is going to be much harder. So anyway, that's that's part of, I think, part of the reason, but it's not completely the reason, but this is a part of the reason that I think can help to appreciate why parameter tuning is so hard. Now, I wanted to explain something like continuous formulation, meaning that we kind of like formulate machine learning as a PDE problem. And then by discretizing these PDEs, we come up with machine learning algorithms, real machine learning algorithms.
Wait, could I just ask a quick question? So parameter tuning, is that the theta people refer to as the theta?
No, that's not the that's
so what is
parameter tuning? Parameter tuning meaning hyperparameters. So the choice of m, the choice of n, or n is pretty much fixed, but the choice of m, for example, if you have 5 layers, how many neurons in each layer? And then the parameters, the hyperparameters in the training algorithm. So like the learning rate, how do you initialize the algorithm? How do you choose the learning rate? So these are called hyperparameters. These are not the parameters like A and J that we try to find in the training in the training process. So these hyperparameters, we have the freedom to choose. And if we choose it in a bad way, then we get bad results. So we have to tune these pretty, heavily in order to get good results. And that's because the performance is very sensitive. We have these phase transition in terms of the performance. That's.
Well, is this related to the algorithm you use to find the optimization, the gradient descent, or is that something else still?
For different algorithms, you have a different phase diagram, but generically you have this kind of a situation.
Okay, thanks.
I wanted to explain this continuous viewpoint, like formulating a machine learning as a PDE problem and discretize the PDE, and then you get the good algorithm. But my time is up, and it's not. If you're interested, you can always look at my webpage. My webpage has some review articles, which I think for people who are interested could be interesting. So the first paper is about the review of the theory. The second paper is a review about using, solving high dimensional PDEs. Third review paper is about, developing new physical models using machine learning. So what I want to say, conclude, is that it really changed the way we deal with functions. And functions are very fundamental objects. So that, it's no surprise that they're going to change a lot of things. And I think the right mathematical picture is numerical analysis, but it's not the usual numerical analysis. It's high dimensional numerical analysis, like approximation theory, solving PDEs, approximating dynamical systems, approximating probability distributions. It's all numerical analysis, except it's in very high dimension. So I think that's the right perspective. Okay, I want to end the talk here. Thank you very much for your attention.
Thank you very much for a really beautiful talk and an inspiring talk. I think you have opened so many things up, and it gave me the idea that maybe machine learning could be useful also in studying quantum field theory, which is something I'm very familiar with a very large number of dimensions. So
I think I have a student who's working on renormalization group, using machine learning to do renormalization group. So sort of related to quantum field theory.
yes, there you want to pick out the important degrees of freedom in this huge space.
Yeah.
So I think that there will be many questions and a great deal of discussion, but before going on, I'd like to ask if we can put your complete set of slides on the website so that people can see all the things that you didn't cover and also all the references you have there.
Sure, I'll be happy to send it to you.
Great. So maybe I'll open the forum for discussion. When you ask a question or talk, please turn your video on so we can see you.
Hi, Professor. Can I have a question?
Sure.
So you did not talk about how we choose the probability in the maybe the two-layer neural network or the Monte Carlo algorithm. So how can we choose the probability for that?
That's training. So by training, we actually, the parameters we find in the end is actually a sample of that probability distribution.
Okay. Okay. So we not only just train the parameters, we also train the probability distribution.
The parameters is really so what I'm saying is that the parameters themselves, the values of parameters themselves, important is the for these parameters. Not important because if you train the second time, different set of parameters, you're not going to recover. If you train, you get a million set of distribution.
So I'm afraid you're dropping out again on the audio, but I hope we can continue.
Can you? I'm really sorry that this is the internet, so it's not
yes,
so
you're in
great.
a hotel, so we can't depend upon the internet. So let me ask a question. Have you been able to improve on the results of AlphaFold on protein folding?
We have not, but we're working on it. We're
That's
working on
very
it too.
interesting.
Yeah. So okay, that's an interesting question. So AlphaFold is purely data driven. It doesn't use any dynamics. Whereas what we did, well, we didn't try to solve the protein problem, but for our thing was really based on dynamics. So there is a huge possibility to combine the two. In order to do that, we first have to recover our version of AlphaFold too. And that's what we're working on. So hopefully we'll be able to.
We'll look forward to your results. Eric, you have a question.
Yeah, hi. Thanks very much for the talk. It was very interesting. Just going back to the discussion on tuning. So my view, and it might be wrong, right, is that when you tune, you're tuning from data and you're using sampling, and essentially this is why we end up with the discrete finite approximation of the continuous functionals for tuning. Are you saying that if we were able to infinitely refine this approximation, we will end up with your continuous view in the one of the last graphs you presented?
Yeah, I would say so.
And okay, and can we measure practically? Can we measure how far we can be? How fine the tuning can be achieved, how finely can it be achieved given the data set?
It's hard.
Yeah, I thought so.
In practice, that's hard. In practice, that's hard. Yeah.
Okay.
We can cook up examples for which we're going to do this, but I don't think that's what you have in mind. Practice, that's hard. Well, at least right now, it's not.
Okay. Thank you.
Mm-hmm.
Sorry,
Don't try.
yeah, can I ask, if I understood you correctly, in Monte Carlo and hybrid Monte Carlo, you don't expect an improvement due to machine learning, that those are already optimized in some sense? Am I interpreting that correctly?
I didn't actually say that, but I think that's an interesting.
No, I appreciate that, but that's why I'm saying, am I interpreting it correctly?
No, I didn't say that, but that's actually an interesting point. Whether you can improve Monte Carlo I mean, I use Monte Carlo as an analogy because we're solving high dimensional problems. So machine, Monte Carlo is a high dimensional problem. I use that as an analogy, but whether one can use machine learning to improve Monte Carlo, that's an interesting question. I mean, there is a possibility because of yeah, I'm not sure. I shouldn't say anything, but I think that's an interesting point.
Thank you.
So are there other questions?
Yeah, well, I wanted to ask you, Weinan, about, there were some headlines about improving simulations for fluid dynamics, Navier-Stokes using these ideas. When I talked to some of the experts, they decided that no, this doesn't really worth anything. I mean, Srini didn't think very much of it, but do you have any opinion about whether these ideas, problems in fluid dynamics can be better understood through machine learning?
Okay. If you want to solve Navier-Stokes, if you just want to solve Navier-Stokes, at this point, and if you have a really rather simple geometry, at this point, I don't see any improvement at all.
Mm-hmm.
If you want to do, if you have a complicated geometry, very complicated geometry, then there's some, machine learning can at least alleviate the complexity of writing the program a lot. So because there's, it doesn't require a mesh, it's mesh free. Now there's another idea that's been discussed, which is turbulence model.
Yeah.
I tried very hard. I would say it's not successful yet.
Mm-hmm.
And there is a real obstacle. But many times when we do CFD, we not just want to see the flow. We really want to optimize something, do control and optimization, do design. There's lots of room there with machine learning. Mm-hmm. Essentially, right now we cannot, we just try. Then we change the wing, like what Tony Jemison did, right? The design of wing profile.
Yeah.
Each time we that's very, very inefficient process. That kind of process can be, changed fundamentally with machine learning.
Thank you.
So it's also very beautiful that you can prove theorems with the ARIS.
Well, these are easy theorems. I mean, the real hard theorems are about the SGD, that's the hard part.
Are there more questions? Well, if there are no more questions, I want to thank you once again, and also invite you to come back when you're not in the hotel so you can give us another talk about your newest results. Thank you. Thank you very much.
Very much. Thank you for, and sorry.
See you next week.
Yeah, yes.